Assalamu alaikum all and good afternoon. This is Adel and I would like to welcome you to our presentation. The topic of our project is the solid state transformer based medium volts drive system for remote area uses. Now these are the outlines of our presentation, problem definition, objectives, engineering methodologies, results, software tool demo, and conclusion. Now the problem starts with remote utilities that are far away from residential areas. However, extending distribution lines to these utilities is relatively costly. Currently, those facilities are using PV systems with conventional transformers. However, this project proposes the solid-state transformer-based PV system as an alternative solution to the power of these utilities. Now, why solid-state transformer? First of all, the use of power electronics converters-based transformer is a very attractive technology because of the quick advance in power electronics nowadays and the emergence of silicon carbide switches that have high capabilities in terms of voltage levels, in terms of switching frequency, better than its previous alternatives. Moreover, we want to investigate more on this hot research topic of power production and transmission, which would enhance our techniques in power system design, and also come up with new conclusions that could help the academic and the industrial communities in designing this emerging technology. Now, we suggested using the following system powered by off-grid solar PV. Firstly, a boost converter powered from PV system aims to generate low volts DC at maximum power point tracking. Then an inverter used to produce the high frequency voltage. The power transformer is used to step up the voltage to the required level of the induction motor. After that, a rectifier is used to produce the high volts DC bus. And lastly, a controlled inverter is used to produce a 60 Hz high voltage level to drive an induction motor. Now I will leave you with my colleague Mohammed to elaborate more on the objectives part. Thank you.
Thank you, Adel. Now I will talk about the objective of our projects. Our project has four objectives. The main objective is to investigate the solid-state transformer, while the second objective is to design the three-phase solid-state transformer, and we are here focusing on high power and high frequency transformer. The third objective is to verify our design using Simulink and finite element program. The fourth objective is to create a standalone software for transformer design. Here I will talk about engineering methodology and tools that used to accomplish our projects. First of all, our project has four stages: the transformer design, controls, power electronics, and the creation of software tools. And these stages are distributed among team members as shown in the figure. For the tools that we use to accomplish the stage of our projects, we use MATLAB and Maxwell. For the MATLAB, we used it to calculate the transformer dimensions, Simulink to simulate the whole system including power electronics and control system, and we use MATLAB App Designer to create software tools that visualize the dimension of our transformer. And we use Maxwell to verify the transformer design using finite element analysis. Now regarding the engineering methodology, first we define our problem, then we decided to go with the three-phase solid-state transformer, then we did a literature review and define our specification, then we proceed with the design and verify our design. Finally, we integrated the system and obtain our result. Now regarding the transformer design methodology, we came up with this flowchart to have clear view of the design procedure, starting off with the primary data which relate to our project specification. We proceed to calculate the power and current, then turn ratio and winding calculation. After that, we calculate the core dimension and coil former. Then we proceed with the coil dimension and single phase equivalent circuit. Finally, we end off with the calculation of the losses of our solid-state transformer. Now, I will leave you with my colleague Khalid to elaborate more in the result of our projects.
Alright, thank you Mohammed. Now I will showcase the transformer design result as per the flowchart shown earlier. This part covers turns calculation, cable sizing, dimensions of core, bobbin, and coil. After that, the equivalent circuit and efficiency, and finally the transformer design verification. Starting with the turns calculation, we obtained 6 volt per turn and turns ratio about 0.09, number of turns in the primary 64, in the secondary 729. After that, we calculated the primary current, which was about 152 amp in the secondary, in the primary, then in the secondary about 14 amp. Then we sized the primary wire to be 38 AWG with approximately 8000 strands, while the secondary about 731 strands. Now after the completion of this part, we proceeded to the core design. First of all, I would like to mention that this drawing is not accurate to scale, just for the purpose of illustration. Now regarding to the core dimensions, we obtained the overall width about 36.7 cm, overall height about 36 cm, while the thickness about 1 cm. Of course, more details are shown here, such as the window dimensions, tongue width, and yoke height. Also, the cross-sectional area is about 1.36 cm squared. So we have a thin core because we are operating at high frequency. Also, we can imagine the core size like the laptop size. Now, after the completion of the core dimensions calculation, we move to the next stage, which is the bobbin design. We used the bobbin or the coil former to isolate the windings from the core. So, regarding to its dimensions, we obtained the overall height about 33 cm, which is approximately equal to the window height shown in the previous slide, because the bobbin should fit inside the window. Overall width about 17.75 cm, and length, as you can see in the right side, 17.5 cm. Also, we can see here more details like the inner height and the frame width where we wrap the windings. And once we have the bobbin dimensions ready, we can proceed to calculate the coil's dimension. As you can see here, this is the arrangement of the winding from the top view. We have the core leg in the center, then low voltage insulation in brown, primary winding in orange, secondary winding in gray, and high voltage insulation in black. And this is the side view. We obtained the coil height about 32.5 cm and copper thickness, including the insulation, about 7.8 cm. So at this point, we completed the result of the dimensions, and we will move forward to obtain the equivalent circuit parameters and efficiency. In this part, we calculated R1 and R2, which represent the copper loss, and they are 0.03 ohm and 0.9 ohm respectively. L1 and L2, which represent the leakage inductance, and they are 0.4 microhenry and 48 microhenry approximately. Also, the magnetizing branch, RC about 2 kilo ohm and LM about 0.9 millihenry. After that, we calculated the equivalent impedance referred to the primary side, as you can see here. Then we proceeded to calculate the core loss, which was approximately 24 watt, copper loss 772 watt approximately, which will sum up to 796 watt as the total loss. Then we calculated the efficiency of the transformer, which was approximately 99.2%. Then we moved to Simulink and we modeled our transformer according to the calculated equivalent circuit parameters. And we obtained the line voltage about 4.12 kilovolt, current about 13.75 amp, while the efficiency 98.15%. And we accepted the result since the error less than 5%. Of course, we proceeded to finite element analysis and we modeled our transformer based on the calculated dimensions of the transformer as shown in previous slides. So this drawing is accurate to scale. Now we obtain the secondary voltage about 4.26 kilovolt, while the desired value about 4.16 kilovolt. Regarding to the core loss, we obtained it from finite element program about 28 watts at steady state, while the approximated one was 24 watts as shown in the previous slide. So we are getting an error less than 3% approximately. Alhamdulillah, this is the end of transformer design result, and now I'm gonna leave you with my colleague Saleh. He will walk you through the simulation result of the power electronics converters. Thank you.
Thank you to my colleague Khalid. Now in this part of our presentation we demonstrate the simulation results. The simulation results divided into 5 stages as follow. The first stage is the boost converter input-out waveforms. The second stage is the high frequency inverter output waveforms after and before filtering. The third stage is the rectifier output waveforms, and the fourth stage is the low frequency inverter output waveforms after and before filtering. The final stage is the integration part. The first stage is the boost converter. As we can see, we have the input waveforms in the left hand side and the output waveforms in the right hand side. Also, we can notice that from the table that for the input DC voltage we obtained very close value to the desired value with the error of 3.06% and 0.9% for the output DC voltage, and with the 0.3115% of ripple factor. Regarding the second stage, which is the high frequency inverter, we have the output voltage and current waveforms before filtering, as we can see with the harmonics, and now we have the filter out voltage, and current waveforms. From the table we obtain very close value to the desired value with the error of 0.316% of output RMS voltage and 0.04% for the output RMS current. Third stage is the rectifier. As we can see in the left hand side we got the output waveforms, and from the table we obtained 0.05% of error for the output DC voltage and 0.118% for the output DC current and 0.2% for the output power. Regarding the fourth stage, which is the low frequency inverter, we have the output voltage and the current waveforms before filtering, also with the harmonics, and now we have the filtered output voltage and current waveforms. From table we obtained very close value to the desired value with the error of 0.5% of error output RMS voltage and 2.08% for the output RMS current. Regarding the final stage, we have divided the integration part into 3 stages as follows. The first stage is the high frequency inverter with the high frequency inverter with the high frequency transformer. Also, we can see that from the table we obtained 4.2% error of the output RMS voltage and 2.74% for the output RMS current. The second stage is the high frequency inverter associated with the high frequency transformer with the rectifier. From the table we notice that we got 3.35% of error for the output DC voltage and 1.59% for the output DC current. Regarding the final stage, we put the high frequency inverter associated with the high frequency transformer with the rectifier, and with the final stage, which is the low frequency inverter. From the table we got 0.26 for the load voltage and 0.79% for the output load current. Thank you. Now I leave with my colleague Meshal.
Thank you, Saleh. And now we will move on to showcase the created software tool. Okay, so here is the main user interface of the software tool. To the left we have the input parameters and the output parameters, and to the right we have what we call the workspace. The users need to enter 5 input parameters, which are the input and output voltages, the rated power, the frequency, and the flux density. Additionally, we have 2 optional input parameters, which are the relative permeability and the power loss density. These 2 are optional because they are only used to calculate equivalent circuit parameters. Also, the users will get a tooltip indicating that these 2 parameters are indeed optional, as you can see. Now, I've already preemptively entered these input parameters as per our design specification of the transformer. And now, once I push simulate, the output parameters will be calculated and displayed here in the output parameters section of the software tool. These output parameters are subcategorized into different categories. For example, we have the transformer parameters here, the equivalent circuit parameters, the winding parameters, the core parameters, and the coil dimensions. Also, the software tool will offer to display reference images when needed. As an example, we have here in the equivalent circuit parameters this button which will display a reference image in the workspace that will indicate what each of these parameters mean. Also, we have the same option for the coil dimensions with this reference image. Another important feature of the software tool is that it helps in visualizing the design. And we have three options for the visualization of the design. Either to view the 3D model of the base core by itself, or to view the 3D model of the base core with the bobbin or the former, or finally to view the 3D model of the full core, which indicates the core, the bobbin or the former, and the windings. And also these 3D models are interactive, meaning that the users can rotate them, they can zoom in, zoom out, or perhaps measure some distances, and they can also save these 3D models for future use if needed. Now, another use of the software tool is to perhaps verify some equations or study the effect of some parameters on the core size. As an example, we know that the frequency is inversely proportional to the core size. So now, once I change the frequency from 100,000 to say 20,000, I expect that the core will be bigger. And now once I push simulate, as you can see, the core did indeed get bigger. And also this change happens in real time. So wherever you are in the software tool, the displayed 3D model will be updated. As an example, if we go back to the 3D model of the full core, and now we change the frequency back to 100,000, and I push simulate again, the 3D model will be updated accordingly in real time, and also the output parameters. So that was it for the software tool demo, and now we go back to the presentation for the conclusion. Alright, so to recap, we have designed a high-frequency 3-phase solid-state transformer and showcased the results and all the related parameters. We have also provided a systematic design procedure for solid-state transformer design. And this systematic procedure will be greatly helpful to the scientific community because of the noticeable gap in the literature. Finally, as I have just showed you, we have created a standalone software tool that will help the users to obtain several design parameters, and it will also help in visualizing their design. Now, in terms of the conclusion to this investigation, for the specified application, we have concluded that the solid-state transformer-based system is not a preferable replacement for the current conventional transformer-based system. This is due to many reasons, such as the cost. The cost of the solid-state transformer is substantially more than the conventional transformer, and this is due to the added cost of the power electronics components, as an example. Second of all, the overall efficiency of the solid-state transformer is expected to be lower than that of the conventional, and this is also due to the power electronics components because the heat dissipation of the components is expected to hinder the overall efficiency, especially at high frequency. Next, we have the issue of availability. Market availability of the power electronics components is lacking, and this may cause some issues when some components fail and need to be replaced. Finally, complexity. The design of the solid-state transformer is much more complex than the design of the conventional. Specifically, the control of the solid-state transformer-based system is something complicated and is considered a challenge. Now, we have some recommendations for the future work and improvements on this project. To further improve this project, some aspects that were not considered in this project could be further investigated. First of which is the implementation challenges. If this project were to be implemented, then the implementation challenges need to be addressed. These challenges include, as an example, the aforementioned component availability. Another one is the protection, which means the protection for overvoltage and overcurrent and so on. Further research is needed in this area to improve the protection of the solid-state transformer. Finally, economic feasibility. This area needs to be addressed in order to possibly find a way of reducing the high cost of the solid-state transformer. Now, although we concluded that the solid-state transformer is not suitable for this application, the area of research in solid-state transformers is still advancing, and it is also forecasted that it will grow in the near future. And therefore, we hope that our project will be a great contribution to that growth. Thank you all for listening.